Welcome to Periodic Table, Part 2. Our objectives for this part of our discussion of the periodic table will include a description of the information that can be obtained from a periodic table, some classification of the elements based upon the electron configuration, again using the information obtained from the periodic table, and distinguish between representative elements and the transitional metals. Along with this, we will look at some of the properties of each of these. When we look at a periodic table, we see that there are squares, and each square has a single element in it. Inside this element, or inside this square, we see the chemical name, the element name, the element symbol, something about the nature of the element, and information about the structure of that atom. It also provides information about the state of matter that the element is usually found in and the electron configuration. When we look at a periodic table, we see a square that looks something like this. It has the element name, state of matter, the atomic number, the symbol, and the atomic mass. These are the basic bits of information that a periodic table would have. Some of the more advanced tables would have things like the melting point, freezing point, and the crystalline structure, if there is one. The periodic table is grouped or arranged in groups and periods. The columns are called groups or families. They list elements that have similar chemical properties. The groups may also have names to indicate something about the characteristics of the elements in that group. For example, alkali metals, alkali earth metals, and halogens are all individual families. Alkali comes from the Arabic word meaning the ashes. We find sodium and potassium in wood ash, usually found in campfires and things of that nature. Alkali metals are never found in nature in a pure state. They react with the oxygen in the atmosphere very quickly and form an oxide. When added to water, these metals produce a basic solution, hence the term alkali for basic. They also tend to react vigorously when added to water.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Again, alkali metals, they're in group 1A. It's located here on the periodic table. These all react violently with water. Alkali earth metals, 2A, located here. Group 3A, located here. Each one of these columns shows very similar chemical properties. Group 4A, sometimes known as the carbon family. Carbon is the first one on the column, and they all respond equally in similar fashion. Group 5A. Group 6A. Group 7A. Group 7A is called the halogens. They are for the most part gases. Halogen comes from the Greek words halos, meaning salt, and genesis, meaning to be born. Or when they combine with the alkali metals, they form a salt. Just think about this. Sodium chloride. Sodium is an alkali metal. Chlorine is a halogen. When they come together, they form sodium chloride or table salt. We can also use chemical means to separate them and form these compounds, form these elements from these compounds. The most common halogens are chlorine, bromine, and iodine. Again, if you will think back to part 1 when we talked about the rule of 7, these are 3 of the gases. Group 8A, located here. Group 8A is called noble gases. They are all gases, but they have a full valence shell, so they do not want to react with anything else. The electron configurations in groups. Now remember, we said that they have similar chemical properties. The electron configurations, the number of electrons in the valence shell, is some indication and has a bearing upon their chemical properties. So we can sort these out into noble gases, representative elements, transitional metals, intertransitional metals, all based upon their electron configurations. Representative elements. Elements in groups 1A to 7A. We find that these have a wide variety of chemical and physical properties. They are for the most part elements, or metals. Most of them are solids. There are a few that are gases at room temperature, as we have seen, and one, bromine, as well as mercury, are liquids. The transition elements. These have the highest occupied S sublevel and a nearby D sublevel containing electrons. and they are located here. Now remember, when we get up to the 3s third level and the fourth level, 4s fills up before the 3p or the 3d. These are the transitional elements. The highest occupied sublevel in the inner transitional elements are S and a nearby F. These elements or these metals are located here. Now the question was, why don't we have them included as part of the periodic table? Why are they set off by themselves? If we had them set up in where they would be fitting, the periodic table would be so much longer, and it would throw the elements and the periods off for some of these. Another pattern that can be seen in the periodic table is a series of blocks that corresponds to the highest occupied sublevel. So when we look at the periodic table, the representative elements have the S and the P. The transitional elements have the D, and the intertransitional elements have F as the highest shell with some electrons located in them. In conclusion, there's a great deal of information that can be obtained from the periodic table that we have today. Some have likened it to a pocket-sized encyclopedia of chemistry. So much information can be gleaned just from this periodic table. Thank you.